Now I request Mr. Abey Jacob, and his topic is approach to post-quantum cryptography validation. So over to you.
So, good morning, everyone. So today our paper is topic is approach to post-quantum crypto validation. So here we are just talking about how to validate post-quantum algorithms. What would be our approach as such? So we are working in the crypto module validation lab. So so in the post-quantum PKI project as such, so we will be validating the post-quantum algorithms. So I'm Smita and Dr. Abey Jacob. Together we are presenting this paper. So this is my agenda, introduction. Next, I'll be discussing about the brief introduction I'll be giving about NIST FIPS 143 ISO 19790. Crypto module validation process and crypto algorithm validation process, post-quantum algorithms, and MLKEM crystal fiber. What are the parameters? What are the auxiliary functions? Kyber PKE, Kyber MLKEM, and test procedures, some validation reports which we have generated in our lab. So NIST, under NIST, we have 142 validation process was carried out for crypto module validation as such. So this includes validation for crypto module, including hardware, software, or firmware for any US agencies. So now this one NIST has moved to 143, which aligns with the ISO 19790. So we are also adapting to the ISO 19790. So from now on, we will be validating the crypto modules with respect to 19790. And under FIPS 143, which supersedes 142, which aligns with 19790, there are 11 cryptographic security areas. So first one is cryptographic, like when we validate a module, we have to validate the module with respect to these 11 security areas. So first one would be cryptographic modules with specification, cryptographic module ports and interfaces, roles, services, authentications, software and or firmware security, operational environment, physical security, non-invasive security, sensitive security parameter management, self-test, life cycle assurance, and mitigation of other attack. So if a module has to pass ISO 1970, it has to comply to all these 11 security areas. And the relevant ISO standards for crypto module validation is ISO IEC 19790. So this talks about the security requirements for cryptographic modules, and ISO 24759, 24759. So this talks about the test requirements for cryptographic module. So these are nothing but test requirements, in the sense what exactly the lab has to do. Like what are the information vendor has to provide to the lab, and what the lab tester has to, how he will be operating the modules, and like how he will be validating the modules. All will be explained in this ISO 24759 759, and both the vendor come tester in the lab has to follow this standard. Basically, this is called the derived test requirements. And we have for crypto module validation, prerequisite is crypto algorithm validation program. So in this CMVT lab, it generates some test vectors. They share the request file, which we call, which is an input which should be given to the module, and output, which in the form of response file, has to be generated by the module. So this request file will be shared to the vendor. He will pass the request file to the module. He will generate the response file, and he will share to the lab. So we will have the answers for the request file which we have sent to the vendor. So what we will do is we'll compare with the response which is there in the lab with what the vendor has sent to us. If it matches, then we tell the vendor he can bring this module to the lab for validation. So this is how the process goes on. So this is how the communication happens between CMVT lab and the vendor. CMVT lab sends the request file to the vendor, and the vendor in turn sends a response file to the lab. And expected response file, which is compared with the received response file, and if it passes, we'll ask the vendor to bring it to the lab. And under post-quantum algorithms, after 2016, NIST started call for quantum algorithms, as we all know. So after round 3, it selected 3 algorithms. So NIST has finalized FIPS 1, 203, 204, and 205. So FIPS 203 is for MLKEM, that is crystal Kyber, which is a variant of crystal Kyber, and MLDSA, which is crystal dilithium, which is based on Sphinx, and SLDSA. So today I'll be talking about the Kyber algorithm. So this MLKEM is derived from the crystal Kyber KEM, and it is a part of crystal suite, that is cryptographic suite for algebraic lattice suite. So it uses module learning with errors over polynomial rings, which is represented as ZQ of x and x to the power of n plus 1. And for Kyber, n and q are fixed, that is n is 256 and q is 3329. And it is standardized into 3 parameter sets. One is MLKEM 512, MLKEM 768, and MLKEM 1028. And it falls into the NIST security levels 1, 3, and 5. So it corresponding to AES 128, 192, and AES 256. So these algorithms are designed to ensure long-term security even against future quantum computing threats. So this is the basic key encapsulation mechanism. So here we can see Alice and Bob. So Alice will use the key generation algorithm and generate a decapsulation key, that is DK, which is private key, and encryption key EK. So EK encapsulation key will be shared with the Bob, and Bob will use the encapsulation algorithm. He will generate one shared secret key K and ciphertext. This ciphertext he will share with the Alice. Alice will use the decapsulation algorithm and generate the decapsulation algorithm and some random parameters and generate the shared secret key. So at the end, this K and K dash should be same. So without actually sharing the key, they are able to generate the shared secret key, similar shared secret key on the both the sides. So this is how the basic KM works. And for crystal Kyber algorithm, there are some parameter sets like for Kyber 512, NIST level 1, it is NS 256, QS 3329, K is fixed to 2, eta 1 is 3, eta 2 is 2, DU is 10, and DV is 4. Like this, these parameters are fixed. This has to be used when we go for Kyber 512, these parameters has to be used. So when we use this, we get the encapsulation key in bytes as 800 and DK 1632, cipher as 768, and shared key will always be 32 bytes. So K specifies the sizes of the vectors in PKI generation, which is denoted as S and E, and also the size of matrix A cap, the vectors of R, E1, all this are derived by the parameter K. And eta 1, it specifies the binomial distribution for generating specific vector S and E during PKI generation, as well as the there is a random R parameters to generate, that also eta 1 is required. And eta 2, it specifies the binomial distribution for generating particular vectors like E1 sample vectors, E1 and E2 in PKI encryption. And DU and DV, it specifies the input for operation like compress, decompress, byte encode, byte decode, which are utilized in PKI encryption and decryption. So there are some auxiliary function which are used in Crystal Kyber, like functions J and S, J and S, which is nothing but the SHA. Basically, SHA is used, which takes a variable length input and produces a 32-byte output, and function G, which takes one input and produces two 32-byte outputs, and extendable output function. This is the actually version of shake. So that this takes 32-byte input and produces a 64 into eta bytes. And central binomial distribution, it functions in Kyber to produce the secret key S and the error noise vector E in the form of the polynomials. And entity number theoretic transform. So here it is basically used for multiplying large rings, large polynomial in the rings. Basically, this uh, in Kyber, all the polynomials is represented on the ring. So this entity speeds up the multiplication process of the large polynomial, and compression and decompression. This aids in decreasing the overall parameter size, and thus, like it is used for to discard certain lower bits from the public key and ciphertext. And encoding decoding, it is used for the byte encode and byte decode algorithms, which are employed for serializing and deserializing arrays of integers under modulo M. So this is in Kyber we have PKI, that is public key encryption, which is used as instantiation for KEM. So the under PKI we have key generation, encryption and decryption, and which is instantiated to MLKEM, that is key. There also key generation happens with the input of key generation from the PKE, and encapsulation and decapsulation. So these are the algorithms which are involved in that. And when we go to the Kyber PKE, random input is some random D bit, which is of 32-byte array, and output is encryption key, EKPKE, and output is decryption key, DKPKE. So as we can see in this, we are generating some 32-bit random byte D, and we are hash of D is done, that is G of D, which generates a public seed row and sigma, which are each 32 bytes. And matrix A is generated from the XOF of row I and J, and then sample entity is done on that to generate a vector A, and this vector A is stored for the later computation purposes, which we do it in the below, where tcap, where we generate a linear equation. Tcap is equal to a cap s cap plus e. So to this for this one, a cap values of a cap is polynomial values of a cap vector is stored, and we generate a secret message like S of I, which is the vector form, and we error the we generate E of I again with the same process, S of I and E of I, and then S cap and E cap is generated, and then linear equation A cap into S cap plus E cap is generated. This is nothing but the error polynomial which is added to the linear equation to make a computation even more hard actually. So and then byte encode of tcap concatenating the public seed row is done to generate the public encryption key, that is EKPKE and DKPKE. So next, if we go for PKE encryption algorithm, this uses the input like encryption key, which is obtained from the PKE key generation. It is given as input to the encryption algorithm, and here input is EKPKE, and input message M of byte 32, and again randomness R is another input which is generated by the random bit, and output ciphertext. And here this DUK plus DV, these parameters are taken from the parameter set table, And here again, we actually decode the public key which is generated and generate the TCAP. Then again, we generate the row. And then again, A-cap vector is generated. And sample R and E1 vector and E2 vector is generated. And again, entity of R is done to generate A-cap, R-cap. And U and V are generated. By compressing U and V, we get the ciphertext C1 and C2. So this is this C1 and C2 again. It is given to the decryption PKI decryption algorithm, which uses the input decryption key, that is DKPKE, and cipher input is ciphertext C and output is message M. So here we decrypt the ciphertext messages which is obtained from the PKE encryption algorithm C1 and C2. And here we decompress a bytecode and decompose to produce U and V vectors, and then we obtain a message M. So this the output from the PKE key generation is given as, this is the key generation KEM key generation algorithm. So here, whatever input output we get it from the PKE key generation, that is given as input to this particular algorithm. So this takes generates an encapsulation key and a corresponding decapsulation key. So output is encapsulation key and decapsulation key. So it takes the input PKE, EKPKE and DKPKE from the PKE key generation and generates the output EK and DK. And here key encapsulation algorithm, again, it takes input message M, and it hashes h of ek and concatenates message M, and again hashes to generate two random. One is the random bit R, and another is the secret key K. And PKE encrypt, this input is instantiated from the PKE encryption algorithm, that is EK, M, and R, to generate the ciphertext. And again, shared key is generated with the hash of C and K. Okay, and to generate return the shared key and the ciphertext. So in the decryption, what happens is we just start extracting the DK values, whichever we have obtained in the previous module. And through this, we get the C dash and K dash. So here we compare the ciphertext with the extracted ciphertext. So if it doesn't match, then we do the implicit rejection, or else the shared secretary key will match here, and K dash will be given given to the K. So this is how the algorithm is. It takes the PKE encryption key generation module. It takes Z as input and generates the EKDK. And key Kyber encapsulation, it takes the EK and the message, random bytes 32. It takes and generates the ciphertext C and K, and shared secretary K. And here in decapsulation, it takes ciphertext C and 1632 bytes of decapsulation key, and generates and checks if C is not equal to C dash, it implicitly rejects, and if it matches, then it shares the shared secret key. So for our validation purpose, we need the vendor to provide all the intermediate results of the he is supposed to give the seed, PK, SK, CT, SS, and all the intermediate values of Kyber algorithms, including various sub cryptographic primitives and hash functions. Output of all this he has to submit to the lab. And this shake SHA-312, SHA-3 256 shake, all this will be validated with respect to the SHA validation suit. And TRMG, which the vendor will be using for generating random bits, this has to be validated with the NIST SP 890A. It has to satisfy these standards 890B and 890C. And output of all these polynomial arithmetic functions, encoding, decoding, compression and decompression, compression, all these module functions has to be shared to the lab. And as part of this validation, we are supposed to do side channel analysis also. So we follow the ISO standard 17825, which is based on the test vector leakage methodology. And this is our lab generated outputs. Above is the request file and down is the response file. So this is how we have captured the data, and still we are in the working mode, and still study is going on, and again we are generating the outputs and checking. So it is not finalized. And these are the references. Thank you. Any questions? Question?